Hey y'all, I'm Winston.
My name is Nidhi Walker.
I'm Catherine.
I'm Nick.
Before we begin designing and building our CubeSat, we first had to create mission requirements, or set parameters as to what would determine if our CubeSat had accomplished its mission. We created an overarching mission requirement that the CubeSat and the ground station shall determine the percentage of plastic sheets on the poster board, the amount of each size of plastic sheets, and the percentage of each color plastic sheet on each of the 3 poster boards within the 10-minute orbital phase. After creating this overarching mission requirement, we then created mission requirements for each of the subsystems. First, the camera subsystem that shall take images clear enough to discern the size and amount of colored plastic sheets and shall have a field of view large enough to capture the entirety of the 11-inch by 14-inch poster board underneath the plastic sheet. Following the camera subsystem, we created mission requirements for our Bluetooth communication subsystem. That this system shall send images of poster boards via Bluetooth to the ground station, and that it shall make and send telemetry packets with necessary health information about the CubeSat at least one time every orbit. And lastly, the power subsystem, in which we said that the battery and solar panels shall provide enough power for the CubeSat to perform all necessary functions during pre-orbit, 10-minute orbital phase, and post-orbit. After determining the mission requirements and critical functions that our CubeSat needed to satisfy, we then began designing and building our CubeSat.
Hi, I'm Nick. This is our ConUps diagram. As you can see, we divided our ConUps into pre-orbit, orbiting, and post-orbit sections. During our pre-orbit, our Raspberry Pi is booted up and awaits command to go into the orbiting stage. Within orbiting are imaging and transition states. In imaging, the CubeSat will be directly over the poster board, determined by the IMU. In any other time in the orbiting phase, the CubeSat will be in the transition state. This is when the CubeSat will be downlinking the image data to our ground station to be processed. Once our orbits are complete, the CubeSat will move to post-orbit state. This is where it will be checked and the data will be downlinked. The state is ended once our Raspberry Pi is shut off.
I'm going to be going over our system level block diagram. First off, we have our power subsystem, composed of the solar panel and the battery. The battery is connected to our command subsystem, which is the Raspberry Pi. Our ADCS subsystem, comprised of the IMU, which houses the gyroscope, accelerometer, and magnetometer, and our imaging subsystem, consisting of the camera, both send data to the Raspberry Pi. The power, command, imaging, and ADCS subsystem all connect to our structural subsystem, which is made up of the acrylic panels and brackets. Finally, we have our comms subsystem, which is connected to our Raspberry Pi via Bluetooth, which also connects to our grounding station. Our ground station does image processing and uploads images of plastic to GitHub.
Hi everyone, my name is Jameson, and shown on the right of your screen here is our 3D CAD model. To start things off, the battery will be attached to the bottom panel and the side bracket over here using Velcro we were given in our kits. And the Raspberry Pi and the IMU will be attached to the top panel using nylon standoffs. We basically just used the flat sat we built in the first week. The only thing different is that the camera and the camera holder will be attached from the bottom of the top panel instead of the top of the top panel. So the flex cable of the camera doesn't have to go around the entire CubeSat, and that we can meet the 10 cm by 10 cm requirement. To attach the 4 side panels together, we used 4 aluminum side rails, and to attach the top and bottom panels to the side panels, we used these L brackets that connects them.
Here's the beginning of our build.
Previous to my launch day, I had conducted test runs on my Cubesat. During these test runs, my Cubesat was able to perform all necessary critical functions. These included the IMU detecting at what angle to take pictures, the camera subsystem taking images that were clear enough and actually showed the entirety of the poster board, my Bluetooth communication system, downlinking those images in telemetry packets during the orbit, and my ground station image processing those images to provide correct information about plastic statistics on each poster board. However, on launch day, my IMU sensor was unable to detect when exactly to take pictures. It kept repeatedly giving angles of 255 degrees and 65 degrees. As a result of this, the camera subsystem was never triggered to actually take images, and the Bluetooth communication system was never triggered to send those images and telemetry packets back to the ground station. Possible sources of error include the IMU hardware not working the day of launch, as a result of other magnetic influences affecting the readings that the magnetometer provided. Additionally, before round, the IMU sensor may not have been calibrated properly, which affected the angles that the magnetometer reported to the Cubesat.
This is our first round with Jameson. This is the only round where we got most of our data back via Dropbox.
I'm Catherine, and these are the poster boards my teammates should have seen from images downlinked to our Dropbox. Unfortunately, I didn't get to run our code on my Cubesat during flight day. In the hours before the round started, my Cubesat was able to capture pictures based on IMU measurements and downlink them through Bluetooth as expected. However, I was unable to run the code from boot up, so I had to manually sign into VNC Viewer, which usually takes seconds to open and connect. As I should have foreseen, when we only had a minute to set up our Cubesat, my VNC Viewer decided to take an eternity to load, which means I orbited with a Cubesat that was on but wasn't running any of our code. This outcome could have been avoided by more testing and figuring out a working method for running script on startup.
This was my round. I had problems connecting to the Raspberry Pi via network issues, so therefore it didn't run.
Overall, my orbit went pretty smoothly. I was able to take over 30 images of the poster board filled with acrylic squares, simulating plastic in the ocean. Unfortunately, I was unable to automatically downlink these images to my ground station using Bluetooth due to issues with the automation of Bluetooth file transfer between Linux and Windows 10 computers. For my images of the poster boards, I was able to determine how much of the poster board was covered in acrylic squares, what percent of the acrylic was each color, and the quantity of each size of acrylic square.
Here's the orbit from a camera perspective. One of the most important parts of this mission was image processing. We had to make sure it was possible to detect the different kinds of squares, color, and size. We were also able to automate this via a script, but it only worked under certain lighting.
For our code, we had two files that calibrated the IMU and one that did everything in the orbit, which includes measuring yaw, taking the images at the right time, and sending the images via Bluetooth to our computers. The code worked for the most part, but some of my group mates had technical issues accessing the Pi during the orbit.
Even though we had many successes, we still had a few sources of error on flight day. To start off, my Bluetooth driver started to fail the night before the test. To compensate for this, I switched to a Raspberry Pi to Raspberry Pi Linux connection for Bluetooth instead. Also, our image processing algorithm did not work for every single image.